When a stone falls into a pond, it creates ripples that spread outward from the stone's impact location. The circular shape of the waves is a visual cue that indicates the location where the stone was dropped, even without direct observation. But imagine if we can do the same thing for everyday solid surfaces, like localizing where a ping pong ball hits the table during a game, or localizing a person's footsteps, all by remotely observing the elastic waves these impacts create. Well, imagine no more, because in this paper, we do just that. And just like in the water pond analogy, we can localize impacts beyond the line of sight. So how does our method work? We capture the surface vibrations generated by the impact using the dual shutter camera of Sheinin et al. The dual shutter camera can measure the 2D instantaneous tilt angles at multiple surface points at once. This video on the right visualizes the transient elastic waves created by a knock on an isotropic surface. This video is created by repeating a knock many times and measuring the axial displacement for each surface point using a laser Doppler vibrometer. This visualization shows that the transient elastic waves created by the knock maintain a symmetric structure for a short time duration after the knock. At later times, the elastic wave reach the surface boundaries, reflect, and interfere across the object's surface. We model the elastic wave propagation in the short duration right after the knock and capture the surface tilts with the dual shutter camera at 5 surface points. The measured tilts relate to the instantaneous surface gradient directions. We show that during particular identifiable time intervals, called the stable time intervals, these gradients point towards or away the impact source and can thus be used to recover its location on the surface. To recover the source locations, we develop a back projection based algorithm that accumulates the gradient directions from all measurement points during their corresponding stable time intervals to yield a voting map that reveals the impact source location. We tested impact localization on various materials. For example, here we show the localization results for an isotropic whiteboard and an anisotropic plate of plywood. The difference between isotropic and anisotropic materials is that in isotropic materials, the impact creates circular wavefronts, while the wavefronts in anisotropic materials have an approximately elliptical shape due to the varying speed of sound with the relative angle to the surface microstructure. Let's take a closer look at the ping pong table experiment. As seen in the illustration below, we set the camera to image the table vibrations at 5 surface points located at the bottom of the table. The markers on the top surface visualize the approximate locations on the bottom. Our system can localize where the ball hits the table during a game, using only the measured vibrations and without having a line of sight of the ball or of the player. In this experiment, we localize footsteps using the vibrations they create on the floor. The camera is measuring 5 floor points, and like in the previous experiment, it does not have a line of sight to the walking person. Using the 5 markers, our camera can roughly recover the footstep locations. The recovered locations here are somewhat noisy because this experiment deviates from the assumptions of our model. Specifically, the floor is a non-homogeneous surface and the stepping leg is not a short and localized impulse, but has a spatially wide footprint. Nevertheless, we show that using more markers in non-collinear configurations significantly improves localization. Besides localizing the impact, we also show that the transient vibration's shape contains additional information about the physical interaction. For example, in this experiment, we dropped the ping pong ball from different heights and computed the peak vibration magnitude as a function of height. The plot shows a square root relation between the peak magnitude and the dropping height, which suggests that the ball's peak generated force could be inferred from the vibrations. Moreover, the shape and composition of the impacting object affects the spectral composition of the resulting vibrations. This suggests that the measured vibrations contain cues about the impacting objects as well. In summary, we presented a novel approach to localize impacts on object surfaces by measuring the transient vibrations these impacts create. Our method opens the door for various novel vision tasks, like localizing bullet or bird impacts on airplane fuselages mid-flight, or impacts on ship hulls from dockside, tugs, or other debris, localizing people in building fires, and localizing survivors under the rubble of falling buildings. Thank you for listening.